Hi everyone, today we're going to be talking about one of the most fundamental processes in neuroscience and an MCAT favorite, the action potential. The MCAT expects you to not only know the steps, but why each step happens. That's exactly what we're going to be covering today. So, what is an action potential? Think of it as an electrical signal that a neuron uses to communicate. Just like a text message that travels across your phone, an action potential is how information travels down a nerve cell. Without action potentials, your brain couldn't tell your muscles to move, your eyes to see, or your heart to beat. Before we dive into the action potential itself, we really need to understand the resting membrane potential. At rest, the inside of a neuron is more negative than the outside. We say it's approximately negative 70 millivolts. And there are two main reasons for this. Number one is the sodium-potassium pump. This is a pump that uses active transport, which means it uses energy to pump ions against their concentration gradient. This pump in particular uses 1 ATP to move 3 Na plus outside of the cell into the extracellular fluid and 2 K plus into the cell at the same time into the cytosol. You guys will want to remember these ratios. So notice how it's uneven. There are more positive charges that are leaving than entering, which helps make the inside more negative. But even though the sodium and potassium gradients are set up by the pump, the ions can still move passively through leak channels that are always open. Think of leak channels like open pores in the membrane that are specific to certain ions. At rest, the membrane has more pores or leak channels for potassium than sodium. Remember that there is more K plus inside the cell, and less K plus outside of the cell. This means that the potassium leaks out of the cell down its concentration gradient. Since positive charge is leaving, the inside becomes negative. On the MCAT, you will want to remember that the resting membrane potential is mostly due to potassium efflux through leak channels, not sodium. Now let's walk through the phases of the action potential step by step. Think of it as a sequence. There's the resting membrane potential, there's a depolarization phase, a repolarization phase, there is a hyperpolarization phase, and then it goes back to its resting state. So let's start at the beginning. When a stimulus is strong enough to bring the membrane to the threshold, which is approximately negative 55 millivolts, something important happens. The voltage-gated sodium channels open. Now, as the name suggests, these are channels that are sensitive to changes in voltage. Now, remember that the sodium is way more concentrated outside of the cell than inside of the cell. So when the channels open, sodium rushes in. There are two main things that drive this influx. Number one, as we just covered, is the concentration gradient. Sodium wants to move from the high concentration outside to the low concentration inside. And number two, there's the electrical gradient. The inside of the cell is negative, as we just covered, and sodium is positive, so it's attractive inward. This double force is called the electrochemical gradient. As sodium floods in, the inside of the cell becomes less negative and more positive. The voltage shoots up from negative 70 millivolts to approximately positive 30 millivolts, and this spike is considered the depolarization phase. An MCAT tip would to think that anytime that you see depolarization, think sodium in, and that will really help you go through questions. Now, these sodium channels can't stay open forever. They quickly inactivate once they reach the peak, and at the same time, the voltage-gated potassium channels open up. Now, remember that the potassium is way more concentrated on the inside than the outside. So when those channels open up, the potassium flows out of the cell. These positive charges leaving bring the inside back down towards negative values, and this is called your repolarization phase. So the takeaway is sodium in is depolarization and potassium out is repolarization. The MCAT loves to test this as a cause and effect. Think about it. If the potassium channels are blocked, the neuron stays depolarized for longer. But the potassium channels are a little sloppy. They don't close right away at negative 70 millivolts. Instead, they stay open a bit too long. So extra potassium leaves, and the membrane dips below the negative 70, maybe to negative 80 or negative 90 millivolts. This is called the hyperpolarization phase. This makes it harder for the neuron to find, again, right away. That's one reason why the relative refractory period exists. You need a stronger stimulus to get back up to the threshold. Finally, the sodium-potassium pump and the potassium leak channels restore balance. The pump uses ATP to push sodium back out and let potassium back in, while the leak channels let potassium continue to trickle out. Together, they bring the neuron back to its stable resting potential of negative 70 millivolts, ready for the next action potential. Now, there are a few more concepts I would like to go over before we end. First is that the action potentials follow something that we call the all or none rule. Once the threshold is reached, it fires completely. You can't have a half action potential. In fact, the MCAT likes to test that increasing stimulus strength increases firing frequency, not the size of the action potential. It will always go from negative 70 to plus 35 and then back down to the hyperpolarization phase to the resting period. Number 2 is myelin. Now, we know what happens at a single point on the neuron. Let's talk about how the signal actually moves. This is called propagation. In an unmyelinated neuron, the action potential has to regenerate at every single patch of the membrane, step by step, all the way down the axon. That works, but it's slow. In a myelinated axon, things get much faster. Myelin, think of it like insulation around a wire, preventing ions from leaking out at these points. The current doesn't regenerate everywhere. It only regenerates at the exposed gaps called the nodes of Ranvier. The signal essentially jumps from node to node in what's called saltatory conduction. A good way to picture this: in an unmyelinated axon, you're walking down a staircase one step at a time. With myelin, you're skipping steps, faster and more efficient. An MCAT tip is that myelin increases conduction velocity by preventing ion leakage. And if myelin is damaged, it can lead to serious problems. And I've seen a bunch of passages on the MCAT about this. Now, one last piece that's crucial for the MCAT is the refractory period. After a neuron fires, it has a short recovery time before it can fire again. During the absolute refractory period, the sodium channels are inactivated. No matter how strong the stimulus is, the neuron cannot fire, period. There are no exceptions to this. During the relative refractory period, as we covered over here, sodium channels are resetting and the membrane is hyperpolarized. The neuron can fire again, but as we said, it takes a stronger than normal stimulus to reach the threshold. The MCAT loves this because it explains why action potentials can only travel in one direction. The area just behind the action potential is in its refractory period, so the wave can only move forward, as we can see here. Now let's walk through a question. This was actually a double AMC question that was on full length 1. Now let's walk through it. What is the function of the sodium-potassium ATPase during a neuronal action potential? So we have covered this in detail. We know that it maintains the resting membrane potential. We know that it uses 1 ATP to pump 3 Na plus out and 2 K plus in. And that's pretty much covers the most of it. So let's go through the answer choices one by one. The stimulation of the action potential. When we went through this, I remember talking about how the voltage-gated sodium channels are the ones that lead to the depolarization phase, or the stimulation of the action potential. Now, we know that that's not the sodium-potassium pump, so we can roll this out. Depolarization. This is very similar to the last answer choice, so we can also cross this out. Hyperpolarization of the membrane. Now, remember that this is when the voltage-gated K plus channels get a little bit sloppy. They allow more K plus to leak out than the resting membrane potential. So since this is not about the sodium-potassium pump, we can cross this out. The only answer choice left is D, but let's go through it first. The restoration of the resting potential. Yep, that's it. Remember that the sodium-potassium pump maintains the resting membrane potential along with the potassium leak channels. So we know that this is our right answer. Now, this pretty much covers action potentials. And if you guys want to learn a similar concept related to this, which is also essential for the MCAT, are synapses. Now, if you keep all of these points straight, you'll be ready for almost any MCAT question on action potentials. Thank you.